Hello and welcome everyone to today's webinar. It is going to be an introduction to the standardization of next generation sequencing workflows. And our speaker is Kübra Narci. And this is going to be a two-parted seminar. So today we are going to learn about standardization. And on the 20th of June, we're going to hear the part 2, which is on benchmarking of NGS workflows. Again by Kübra, again 4 o'clock. And if you like it, Kübra and her team are also going to be at the GCB later this year in Hamburg. So if you're there, she's giving a workshop, please have a look and say hello. She's going to look forward to meeting you there as well. And before I hand over to her to talk about actual next generation sequencing today, just a couple of words on GHGA. So we are the German Human Genome-Phenome Archive. And our mission is to provide GDPR-compliant data sharing for human omics data. And this hopefully will then enable the secondary use of clinical omics data in research and enable the translation of research insights to genomic medicines. And obviously, we are not going to do this alone. So this involves diverse communities, computational biologists, geneticists, clinicians, physicians, and patients. And if you would like to learn a little bit more about GHGA, please do go to our website. On our website, you'll also find further resources on our training activities. And that includes all the webinars that we have been holding so far. And on YouTube, you also find a playlist with all those webinars if you want to rewatch them. At the bottom of the page, you'll find a barcode. If you'd like to sign up to our newsletter, then you'll get informed whenever we are planning to hold another webinar. And now coming to today's event. So Kübra, our speaker, obtained her master's in bioinformatics from the Middle East Technical University in Ankara in Turkey. And in the same department, she also obtained her PhD. She then worked as a bioinformatics analyst for Seven Bridges Genomics. And last year in May, she joined GHGA and is working in the workflows work stream and developing workflows for our communities. And with no further ado, I hand over the stage to Kübra.
Good, very well. So welcome everyone to today's webinar, where I am going to introduce the standardization of NGS workflows. So here is the outline to the presentation. First, I am going to talk about what a traditional bioinformatic workflow look like and why it is actually a challenge to make analysis with them, and how we are facing with a growing issue of reproducibility. Then I will quickly go over GHGA goals and objectives, and specifically aligning to workflows. Afterwards, we will be more diving in to standardization of workflows, and mostly I will be talking about components of a standard and optimized workflow. Finally, I will introduce you with the concept of workflow management systems, and I will talk about our favorite tools. And then afterwards, we will make a summary. So in data-intensive science, software tool chains are heavily used as in order to help scientists to manage and analyze their increasing volume of complex data. Here on the right side, a very simple tool workflow starting from quality control using FastQC tool, following by alignment, variant calling, and various statistical extraction steps are shown. Essentially, we connect all those steps, these bioinformatic tools, to make the process automatic. Usually, what we want to get the results as simple as possible in a one click. What we call as bioinformatic workflow is chaining bioinformatic tools to make the process automatic. Although these bioinformatic processes are automated in these simpler workflows, actually they are problematic because they are not adaptable to different setups, since they usually build upon specific versions of tools in the local environments with specific infrastructure needs. Thus, it is not possible, and sometimes it is problematic and sometimes not possible to reuse them, also share them. Luckily, we are calling those systems as traditional right now because we have more optimized version of bioinformatic workflows. Before I switch into talking about them, I want to emphasize that these traditional bioinformatic workflows are actually results of series of assumptions that we make commonly. It is often to ignore the fact that analysis workflows we created won't be used again. But a new set of samples to analyze came around 6 months later. We don't remember the exact settings that we use. Also, the software versions we are using is not stable at all. Even a small change in a tool may cause a dependency error. Suddenly, a lot of tools will produce warnings and errors. And while you are trying to resolve them, it will take a lot of time, actually. Tracing execution history is not easy. Do you remember which version of tools you used in the bioinformatic workflow you settled on? And when did you get the latest updates? It is hard to keep track all of these changes. Usually we think that workflows will work anywhere, but usually it is not the case because the infrastructure needs are different. For example, I cannot share the same workflow that I created on a Mac computer and expect my colleague with Windows computer use it, because this installation of tools won't be possible there. And finally, scalability is an issue in bioinformatics because we are dealing with large volumes of data, and managing those data in a local environment is a big problem. So the biggest challenge in bioinformatic analysis is reproducibility. And the collective endeavor of science depends on researchers being able to replicate, redo, or reanalyze the work of others, which is a non-trivial task to accomplish. In a survey conducted by Monia Bayer at 2016, 70% of responders admitted having difficulty in reproducing experiments proposed by other scientists. But 50% of them, this issue even concerns with their own experiments. Actually, reproducibility is not only a moral responsibility with respect to the scientific field, but lack of it can be a burden for you as well, an individual researcher. Being able to not to reproduce others' work has led to discussions on how researchers can establish routines in order to increase transparency. And the scientific community needed to develop a culture of reproducibility and actually push them, require it for the published claims. A diverse set of stakeholders representing academia, industry, funding agents, and scholarly publishers have come together in order to design and jointly endorse a concise and measurable set of principles, which now they call fair data principles. Fair data and workflows means they are findable, accessible, interoperable, and reusable. Since it is not the main topic for today, I won't go over what fairness is, but I will explain the details of the components ensuring fair workflows today. As GHGA, we are a member of GH4GH, a Global Alliance for Genomics and Health, and we act fair rules. The main aim of GHGA is to establish a federated national infrastructure, a national platform for fair human data. The frameworks for data sharing, protection, and data analysis will be following ethical legal with fair standards. Finally, we will be providing standardized procedures for metadata and for workflows. And today, as a part of workflows team, I will be explaining further how we harmonize bioinformatic analysis to make it fair. Thus, at the end of this webinar, you will be familiar with the components and principles of standardized bioinformatic workflows. You will be learning about metrics in order to measure the fairness and the processes to automate the workflows. And I will be introducing workflow management systems, and I will try to give recommendations and tips for workflow developers. And let's start with the components. If we want our analysis to be reusable, they need to be portable, encapsulating all their runtime dependencies. And by portable, I mean being able to provide others the same run conditions for the softwares, tools, and the workflow itself. There are two technologies to automate the software installation process and ensure portability across different platforms, which are package managers and containerization softwares. Package managers automate the process of installing and configuring the software itself. They enable a user to obtain all the tools, dependencies, which is required to execute a pipeline with a single command. They eliminate the need to locate and manually install all of the tools, which is needed in order to install it. Which is usually have many distinct installation requirements. And examples of these package managers are Hombre, PIP, and Conda with Anaconda and Bioconda. By using those, one can install like FastQC, GATK, BWA as a part of this simpler bioinformatic workflow. Usually through tools distributors. So they are usually available as a single line of command. Containers, on the other hand, are configurable virtualization technology that allows packaging and distribution of pipelines in a self-contained and platform-independent manner. By this way, installation software using package managers can also be packed into an image with its corresponding dependencies. Here, what I mean by image can be considered as a file or a set of files that contain the application with its code itself, and also it is other dependencies, libraries, and bins. After all, you can copy the image around, upload them into the registries, download them, and reuse them. Commonly used software for containerization in bioinformatics includes Docker, Singularity, and Podman. Let's look a bit closer to containers because they are really important. A container is an instantiation of an image, which is essentially composed of layers. And each layer reserved for a tool. meaning when you are installing a software inside the container, each dependency will be recorded as separate layers. And at the end, when you set up your final image, actually it will be set of layers. And when you want to create another image for another tool, common dependencies will be used from the previous one instead of creating again. And at the end, the layers for the softwares will be shared. That is mainly because containers uses the same operating system with the container engine. And that is why these containers are lightweight, which is a very big advantage of containers in order to put them into the registries. And as I already said, after you create your image, you can put them into a server application where those images are stored and can be searchable and be accessible by others. You can make them either public or private. Examples of those registries are Docker Hub and QA.io as a part of biocontainers, and Scilab is also used for Singularity. Besides being portable, another important aspect in standard workflows is stability. Containers provides a level of stability because they are labeled through versions. So whenever you create an image, a tag should be added as an extension to image's name. Since it is a good practice when you commit an image, it is always possible to go back into the history, to the old ones, without losing any important information there. As I already mentioned, nowadays it is a good standard to share these containers through registries. Usually what people do is to put the versions there with their tags. And also tool owners do that. So whenever a software is created, the tool distributor also puts into the container and also share through these registries, where you can also find them, download them, and use them. I actually want to recommend you to search for containers readily in order to use them before you create one, because it will be safer. After you download your image, you can just directly use it or even repurpose it with additional installments on the top of them. Sharing bioinformatic pipelines to the community is actually crucial, and it is a community effort to build a bioinformatic pipeline. Sharing the workflows could help other scientists reproducing their results or reusing its elements. The workflow itself can be publicly archived and made citable through identifiers like DUI. You can put your workflow into websites like Zenodo or Docstore. Here, while adding your workflows, you usually add a good document, and then it will be understandable and findable by others. Galaxy Project and NF Core are other resources where you can find readily pipelines, and there you can also run your analysis readily. Finally, making workflows available through those will ensure its findability, and which is a necessity for fair analysis. Not only containers, workflows can also be versions in order to make them stable. And the most common way of providing stable versions is through Git systems. GitHub, GitLab, or Bitbucket are all valuable services in software development itself. They provide code hosting, a storage platform for version control, and also for collaboration. It lets you and others to work on the same project from everywhere. They are all efficient because the committed changes are saved without any interruption. Basically, using Git Systems, one can create different branches or copies of the stable working version, dependent or independent to one another. There you can open new issues or new tasks and assign to others. One can reply to an issue, get reviews from the ready branches, and when it is ready, it can be merged into another and will be ready for production. Here, multiple level of access is also possible. It provides controlled management over the project. You can give access to specific people, and unauthorized ones won't be able to change the code anymore. So it will be a safe space for code management. Another advantage of GitHub is debugging and running the code itself. Testing the code and building the production can be automated there. Continuous integration test, CI, refers to the build and unit testing of stages for the software release process. So whenever a new revision is made in the branch, it triggers a commit, and which triggering an automated build and unit testing. When it is reviewed and approved with the users, it can be merged safely. And you will know that the code is not broken and all of the tests are already went through. With continuous deployment, it is also same in order to produce the unit testing and build for the deployment. And it is referring for the final production. Whenever continuous deployment is made, it will be ready for the production, basically. Continuous integration and deployment implementations are usually automated for fast development of the project. Being able to run the analysis of data at any scale in a fast and resource cost-efficient way is a key requirement for pipelines. And scalability of pipeline have two aspects: efficient resource management and the ability to handle any size and quantity of input data. Here, for example, I visualized an example run with a total CPU available 8. And considering pair read sequencing, there needs to be 2 run of FastQC. And consider a case that FastQC needs 4 CPU. And if the total available CPU is 8, you can run 2 parallel FastQCs here. And when those are finished, alignment step can run. And here, I just visualized a case where this alignment is parallelized through chromosomes. You know that these chromosomes in size are different. Some of the chromosomes are bigger and some of them are smaller. So bigger chromosomes needs more memory than the smaller ones. By here, when you parallelize them, they can run all together with the need of maximum 8 CPU at a time. So it is really a good research management, and the runtime needed for alignment step will be shortened effectively. So here the process of planning the run and task execution one to one another is called as scheduling. How the tasks are scheduled actually depends on workflow structure and also to the available resource there. And at the end, scheduling also depends on the workflow design. So how did you parallelize your data management and also for the task and the pipeline itself? Developer can decide how to manage resources depending on the size and quantity of the data. Here, there are also dynamical schedulers, which the choice is usually infrastructure dependent. Some systems makes use of Slurm or LSF in order to run jobs locally. Yet there are also cloud systems which can be used anywhere, like AWS Batch and Kubernetes. And at the end, by dynamically scheduling these independent tasks during the execution of the pipeline, will be decrease the unused resource, and it will not be affecting the most resource-intensive steps. Now, let's consider a case where one of the sub-processes is failed. The usual approach of the simpler workflows will be exiting the workflow itself and rerunning all the processes from scratch. Actually, this will be a waste of two important resources, time and process data. Reentrancy is a term meaning caching intermediate results. It allows users to run pipeline from its last successfully executed step rather than starting from the beginning in case of any disruption. Reentrancy minimizes the need for recalculation of the already processed steps, but also it is also needed for the frequent data processing steps like saving reference files or indexing the necessary data files inside the workflow. In order to achieve this, workflow managers use caching to save intermediate steps and data files and comparing them with the expected output in order to generate only the necessary ones. And right now, before I will talk about workflow managers,